Everyone to the first CLEX seminar in our seminar series. We hope to have these monthly. Usually they'll be on a Tuesday morning, but because of Easter, Jerry kindly agreed to give his seminar today. And with that, it is my absolute pleasure to introduce Gerald A Meehl to give our first seminar. Jerry is one of the most eminent climate scientists, I think, in the world. He needs no introduction, but I'll give him one anyway. Jerry is a senior scientist at NCAR in the US. He's also chief scientist at the Cooperative Agreement to Analyse Variability, Climate Change Predictability and the Earth System. His research interests include studying the interactions between El Niño Southern Oscillation and the Asian Australian monsoon, identifying possible effects on global climate of changing anthropogenic forcings such as carbon dioxide, as well as natural forcings, solar variability, quantifying possible future changes of weather and climate extremes in a warmer climate, and understanding the interplay between internally generated climate variability and the response to external forcings. He was a member of the IPCC in the team that won the Nobel Peace Prize in 2007. He's also been on the IPCC in 2001. He received his PhD in climate dynamics from the University of Colorado, and was the recipient of the Jewel G. Charney Award of the American Meteorological Society in 2009. With that, I will leave it there, and we'll introduce Jerry. We'll invite Jerry to give his talk. Thank you very much.
All right, thanks, Sarah, for that very generous introduction. So I'm going to be talking about how the Atlantic and Pacific tropics can be connected by mutually interactive processes on decadal timescales, and the results of this study were published just before the holidays, just before Christmas, in Nature Geoscience, and that's the reference there at the bottom. I want to acknowledge my co-authors on this work. Excuse me, Aishu, Fred, Susan Gokan, and Nan are all at NCAR. Matt is at University of New South Wales. Shane and Julie are at Monash, and Julie's also joined with us at NCAR, and Shang Peng is at Scripps. So the kind of to get to the bottom line of this presentation, does the Atlantic force the Pacific, or does the Pacific force the Atlantic? And to save you a lot of time listening to this talk, I can just basically cut to the chase and say the answer is yes. And I say this with only a little bit of facetiousness, because I'm going to try to present evidence that the Atlantic forces the Pacific and the Pacific forces the Atlantic. In other words, they're mutually interactive. So the whole kind of motivation for this is the field of decadal climate prediction, where you initialize a climate model with observations at a certain time period, you integrate it forward in time, and you try to actually predict the time evolution of the climate system over time scales, say from 1 to 10 years. And you hope that there are decadal timescale processes and mechanisms that actually exist in the climate system that are from these coupled processes, and because they're slow, because they're happening on timescales of years to a decade, the ocean is likely playing a major role. And then if you initialize these properly, then you'd actually hope that you could set these things off kind of going in the right direction, and then they would actually evolve through their own mechanisms and provide predictive skill beyond the first year or two. So what are the usual suspects? This is for the, looking at the literature, there's usually Atlantic decadal variability, the AMO, Atlantic multidecadal oscillation, which is now more generically being referred to as Atlantic multidecadal variability, or AMV. And you can see here that this, in its positive phase, the sea surface temperature anomalies on decadal timescales are somewhat above normal in the Atlantic north of the equator. In its negative phase, they'd be somewhat below normal. And this is a time series of a certain index of this, obviously detrended. And you see that when it's positive, is in the late 1800s, it was negative in the early 1900s, positive in the mid 20th century, negative in the late 20th century, and positive in the 21st century. So you can see one of the limitations of studying these kinds of phenomena is you only get a few realizations of this. You only have maybe 2 full oscillations, or 2.5 oscillations, or 2 fluctuations of this. this variability. So this makes studying this kind of variability really challenging. For the Pacific, we have the phenomena that are variously called the interdecadal Pacific Oscillation, or IPO, or the Pacific Decadal Oscillation, or PDO. They're both basically the same thing. They're defined somewhat differently. The PDO is defined based on SST fluctuations on decadal time scales in the North Pacific. The IPO is for the whole Pacific basin-wide sea surface temperature fluctuations, but the pattern always comes down to looking something like this here in the lower right-hand corner, where this would be the positive phase of what's now being generically called PDV. I'm in this talk, I'm going to kind of be interchanging IPO and PDV back and forth, but this would be the positive phase where the Pacific tropics are positive and it's negative sea surface temperature anomalies to the northwest and southwest in the Pacific. And the PC time series of this second EOF of low-pass filtered observed sea surface temperatures looks something like this. This is one of the possible indices of the IPO, and you can see it's the same thing as the AMOs. You have only a few fluctuations in the observational record, and so we have to depend on climate models a lot to interpret these things. So the question always comes down to, well, how are these related? And maybe if one was driving the other, then this would make our lives easier, because if you could just predict what was going on in terms of sea surface temperatures on decadal timescales in one basin, and that basin was driving variability in the other basin, and the tropics were connected, and therefore we know that if you get tropical sea surface temperature anomalies on almost any time scale, that drives precipitation anomalies and convective heating anomalies, which produces anomalous Rossby waves that go into the mid-latitudes of either hemisphere, and you get these large-scale teleconnections. And so if you could just predict variability on decadal timescales in one basin, and that basin was driving everything else, then that would be great. Then you could just focus on trying to figure out what was going on in that one basin. Everything else would fall out. For example, if the Atlantic was driving the Pacific, one of the main candidates for what is producing this kind of AMO-like variability, or AMV variability, is the AMOC, the Atlantic Meridional Overturning Circulation in the ocean. Then if you could just predict that one thing, then you could get the AMO, which would then drive the Pacific, and then the Pacific would drive, Pacific and the Atlantic tropics would drive the teleconnections, and you'd have a real handle on this prediction problem. But as we're going to see, it's not going to be that simple. It rarely is that simple. So to get at how these things are actually connected in various ways, we have just a short record in the observations. As I said, we've got a lot of issues with the fact that everything's connected all the time with what's going on in the observed system. And so how do you decompose this to figure out what's driving what? So Yukisaka and Changping Shi in 2013 published this paper where they used a methodology that's been subsequently called the pacemaker methodology. And it's kind of an interesting idea, interesting concept, in that you have a fully coupled climate model, atmosphere, ocean, land, and sea ice. But as the climate model is running in one area of the ocean, you can specify the time evolution of observed sea surface temperatures, and then see how the rest of the coupled climate system responds to that. And in their example, they specified sea surface temperatures, observed sea surface temperature time evolution in this box in the Eastern Tropical Pacific. And their headline result from this paper was that this slowdown in globally average temperatures, and the black line here is the globally average observed temperatures. The red line is their pacemaker simulation, and the blue line is their free-running uninitialized simulations. When they ran the pacemaker with the observed sea surface temperatures in the tropical Pacific, they got something that simulated this slowdown that we saw in the observations in terms of global average temperatures. So this was a nice way to try to attribute something that was going on in the system to what we saw in terms of global average temperatures. And so this methodology has been used by other people in various ways ever since. And here's just a few examples from Atlantic pacemaker experiments. And when I say that, I mean that you're specifying observed sea surface temperatures in some way in some part of the Atlantic. Oftentimes these are run with observed sea surface temperatures over the North Atlantic in the AMO region, basically the equator to 60 north. And this is an example from the Rupert Robert et al. Study. They're specifying observed Atlantic SSTs in this area here. And so when these SSTs on decadal timescales are positive, you see that the SSTs in the tropical Pacific are the opposite sign. In other words, they're negative. So you get this opposite sign response between the tropical Atlantic and tropical Pacific when you're driving the system from the Atlantic. This is a paper from Shane and collaborators where they actually did a little bit of a different variant on the pacemaker. They actually used a mixed layer, a non-dynamic mixed layer ocean model rather than the fully dynamic ocean model, specified SSTs, observed SSTs in the North Atlantic, and still got this opposite sign response in the tropical Pacific. Here's another paper from Sun et al., same kind of thing. They were also using a mixed layer, and they also get this opposite sign response when they're driving the system from the Atlantic, and you get this opposite sign response in the tropical Pacific. Okay, so that's kind of just a sample of these Atlantic pacemaker experiments. What about Pacific pacemaker experiments? This is some results from Kumar et al. 2014. And when he was looking at Nino 3.4 SSTs leading by 6 months, the observations show that when the Pacific leads, you get this same sign response between the Pacific and the tropical Atlantic. And this is what they got, and this is the observations. This is their model simulation, their pacemaker simulation. They get the same kind of thing, the same sign response when the Pacific is driving the system between the Pacific and the tropical Atlantic. This is some results from Andrea's paper looking at observations showing that when you get a positive SSTs in the tropical Pacific, you tend to get positive SSTs in the tropical Atlantic. So again, the same sign response. And looking here in the lower right at this result from the Kosaka and Shi, that original paper, this is their trend of SSTs from 2002 to 2012, showing this kind of negative phase of the IPO, these negative SSTs in this time scale. And you can see here a weak same sign response of negative SSTs in the tropical Atlantic. And we kind of looked at this in a different way, where we took the Kosaka and Shi pacemaker runs and did lag regressions, and the black line is the ensemble average from the ensemble members they ran, and you can see that the IPO leads the AMO, in this case with a positive correlation, pretty high positive correlation, which means that when the Pacific is positive, the Atlantic is positive in the tropics. So you're getting a fundamentally different kind of response depending on which ocean basin you think is driving the other. If you think the Atlantic is driving the Pacific, you're getting an opposite sign response in tropical sea surface temperatures. If you think the Pacific is driving the Atlantic, you're getting a same sign response in tropical SSTs in those kinds of experiments. So why do we care about this? Well, and I said before that a lot of the focus of these decadal prediction and decadal variability studies has been on the oceans, because that's where we think the memory lies, and that's where these processes that can kind of drive these slow variations of the system can actually occur. Well, it turns out that if you can get the SSTs in the tropical Atlantic or tropical Pacific, if you can predict those, this will give you an edge on looking at things like precipitation over land. So this is just an example from our paper. It's been a while now, but we actually regressed IPO or correlated IPO index with low pass filter precipitation for the 20th century. You can see when the IPO would be positive, you can imagine the IPO positive here with positive SSTs in the tropical Pacific. You're getting positive precipitation anomalies in southwestern North America, negative precipitation anomalies over eastern Australia, mostly negative precipitation anomalies over South Asia. So just by getting this kind of slow variation in tropical Pacific sea surface temperatures, it can give you information on not only mean, but also extreme precipitation and also heat extremes, because you can imagine that these precipitation anomalies would be associated with extreme heat, especially if you're thinking that you've got reduced precipitation over some of these areas over South Asia and Eastern Australia. You'd imagine that you may be getting higher temperatures with fewer clouds and less precipitation. Same thing for Southwest US. You have more precipitation, be somewhat cooler temperatures, not as many heat extremes, and so on. So this is kind of why we're interested in trying to make these predictions and trying to get this information that can give us more of an edge on looking at what happens over land. Now, in terms of mechanisms, I'm not going to talk about mechanisms in this paper other than to mention there's been work that's been going on. I mentioned the AMOC for the Atlantic. That's a prime mechanism for producing AMO variability, even though there's some issues with exactly how that would work, especially with the main tie between AMOC and the Atlantic is with the subpolar gyre in the North Atlantic, not so much the tropical Atlantic, so there's still some uncertainty there. This was a candidate mechanism for the IPO that we put forward in 2006, and Farnetti et al. Basically reconfirmed or reproduced this result in 2014. But I think the point of showing this is there's a lot of if you think that the IPO is actually a thing, that it's not just a collection of random distributions of El Nino and La Nina events, if you think there's actually a fundamental fluctuation in the background base data on decadal timescales, you can come up with mechanisms that usually involve tropical mid-latitude interactions. In this case, we were trying to say that if the positive phase of the IPO produces these positive convective heating anomalies, this would give a teleconnection pattern. You have anomalous lows in the North and South Pacific. This would weaken the trades and produce downwelling Rossby waves that would build up heat content in the Western Pacific. And then you'd have Kelvin waves that would make this thing transition after these slow Rossby waves that come across. But I think there's a lot of details that you can talk about with regards to mechanisms. The point of this is to show that when you have positive convective heat anomalies with this strong precipitation, you get relatively dry conditions over South Asia, dry conditions in East Australia, and wet conditions over the southwestern US, and kind of the opposite for when you have a negative IPO. You get dry conditions in the southwestern US, relatively wet over South Asia and over Eastern Australia. So that's all I'm going to say about mechanisms, just to say that these processes that are going on in the ocean can produce these sea surface temperature anomalies that you hope to have certain mechanisms that you can capture in an initialized prediction that give you an edge to give you these sea surface temperature anomalies, which can then give you some skill of what's going on over land in terms of mean and extreme precipitation and temperature. So I'm going to we set up two kinds of pacemaker experiments. And I don't want to go into a lot of the details, but they basically are in two classes. One's these idealized pacemakers where you take observations and you basically regress out what you think the internally generated pattern is of sea surface temperatures on decadal timescales for the AMO area in the North Atlantic and the IPO area in the Pacific. And you then put that, your pacemaker then is you put those, that idealized pattern of sea surface temperature anomalies, you superimpose that in the coupled model, and then you let that run for just 10 years. So you use the same pattern, you run it for 10 years, and you can let the system kind of respond to that, and then you can look and see how the rest of the climate system responds to that idealized pattern of decadal timescale variability. The time series pacemakers are the ones that are more familiar from the Kasaka and Shi paper. The original paper was a time series pacemaker where they actually took time evolving observed sea surface temperatures for, in their case, the tropical Eastern Pacific, and just had that go from, and we basically did the same methodology. You run this for 1920 to 2013 with those observed, specified, or nudged SSTs in the tropical Pacific. And then we did the same thing for the North Atlantic, the AMO area for equator to 60 north. So these are the two types of pacemaker experiments we're going to be looking at. We're going to start, and these are all, by the way, the CSM1 from the large ensemble. These are 1 degree resolution, 1 degree class your system model. So these are some results from the idealized pacemaker experiments. And so let's look first at the upper left panel here. And now this is taking the PDV, the plus minus PDV minus, and so we're specifying this pattern in this specific idealized pacemaker between these green lines. So from the North Pacific to the South Pacific, we're specifying this pattern. That's basically the pattern we're specifying for these 10-year simulations. And we're looking at the response everywhere else. So when you look at the Atlantic, when this is in its positive kind of phase, which is the sense of this difference, you can see the tropical Atlantic, both north and south of the equator, has the same sign response to what's going on in the tropical Pacific. So that's kind of consistent with some of those results we saw before that I was showing. And the interesting thing about this is we're getting this really nice teleconnection pattern in the North and South Pacific, this kind of PNA pattern and PSA pattern. You can just see this from the colors here are the sea surface temperature anomalies, and the arrows are the surface winds. And you can see this anomalous cyclonic circulations here in the North and South Pacific, and also anomalous cyclonic circulations here in the subtropics of the North and South Atlantic, which would act to weaken the trades. So the anomalous winds here, you can see these little wind vectors are going, basically they're westerly anomalies that weakens the trades. And that's going to be kind of an important distinction in how this differs between the Atlantic and Pacific pacemakers. If you look at the precipitation anomalies for this, the Pacific pacemaker, the red colors are where you get enhanced precipitation, and not surprisingly, you get greater precipitation over areas with warmer sea surface temperatures. You also see here in the Atlantic, enhanced precipitation basically north of the equator, not so much south of the equator, even though the sea surface temperature anomalies are positive both north and south of the equator. Excuse me. So for the Atlantic pacemakers, now we're specifying this pattern in the North Atlantic here between these green lines. So when the North Atlantic AMV is in this phase, now we're getting this opposite sign response in the tropical Pacific, which is what we saw from the other pacemaker experiments before. This opposite sign response, which is different from the Pacific pacemaker, where we got the same sign response between the tropical Pacific and tropical Atlantic. And the teleconnection pattern that arises from this is coming mainly from these negative, the response to these negative SST anomalies in the tropical Pacific. And it's not very strong. You're getting a little bit of a PSA pattern in the South Atlantic, not so much in the North Pacific. And the precipitation anomalies are, the blue colors are decreased precipitation. So over the cooler SSTs in the tropical Pacific, you're getting mostly decreases of precipitation and a pretty big increase of precipitation in the tropical Atlantic over these warmer positive SST anomalies that we're specifying. So that kind of confirms some of these early results we saw from these pacemaker experiments, which is a good thing. And we can start looking at some of these details. And this is one of the details with this teleconnection pattern. This is the sea level pressure anomalies for the Pacific pacemakers at the top and the Atlantic pacemakers at the bottom. And this gives you a better idea of this PNA pattern and PSA pattern, and how these anomalous cyclonic circulations in the subtropics in the North and South Atlantic could actually then contribute to weakening the trade winds and reducing the pressure gradients that would produce the trades. For the Atlantic pacemakers, you can see that this pattern in the South Pacific is not nearly as strong as it was for the Pacific pacemakers, because the SST anomalies aren't quite as big, but you don't get much of a teleconnection pattern in the North Pacific going over the North Atlantic. So that's kind of a fundamental difference between these two, is how the teleconnection is set up. So when you're trying to talk about connecting tropical Atlantic and tropical Pacific, most of the papers you read will cite the anomalous Walker circulation. This is the depiction of that for these idealized pacemaker simulations. These are cross sections going from basically Greenwich all the way back over to Greenwich here. So the Pacific is kind of in this area here. The Atlantic is in this area here. This is from the surface all the way up to the top of the troposphere. The colors indicate, blue colors indicate anomalous upward motion. Red colors indicate anomalous downward motion. And these arrows that are in here indicate kind of what the flow is doing. And this is kind of a cross section from 5 north to 5 south. So for the Pacific pacemaker, you get this really strong upward vertical motion associated with those positive precipitation anomalies. And you get some downward motion coming down over the Atlantic here, these red colors, and you see this kind of weak downward motion from these arrows here. So we're getting this kind of Walker circulation that's coming in this direction from the Pacific to the Atlantic. Of course, then you're getting this Walker circulation that has strong descent over here in the Western Pacific and in the Eastern Indian Ocean. So that kind of confirms previous results. For the Atlantic pacemaker experiments, now we're specifying the sea surface temperatures here, and we saw positive precipitation, convective heating anomalies. So we get this strong upward anomalous vertical motion here that comes down over here in the Pacific and actually extends all the way to the surface. So you get these strong trade winds here at the surface that contribute to stronger upwelling and ocean heat divergence and cooler SSTs. And so those are kind of the typical things that are looked at when people are connecting Atlantic and Pacific, are these anomalous Walker circulation kinds of things. So it looks like there's a similar set of processes going on here between the Atlantic and the Pacific, but we're getting this kind of different response between the two. So the question is, why would that be? So we looked at, because these are 10-year simulations, we can look at the first 4 seasons of the first year of the 10-year simulation to see kind of how these things are sorting themselves out in terms of contributions from ocean heat transport and net surface heat flux to the temperature. And this is for the Pacific pacemakers here on the left, the Atlantic pacemakers on the right. And so you see that this is the Eastern Atlantic response to this Pacific forcing. And by the time you get to the 3rd season, just looking at the net ocean advection term, which is this blue line here, and the net surface heat flux, the red line, they're both positive, and the black line is the ocean upper layer temperature. And so you can see that it's both the ocean dynamics and the net surface heat flux are contributing to these positive sea surface temperatures in the tropical Atlantic that would give you that same sign response to the positive phase of the IPO in the Pacific. Meanwhile, the Pacific response to the Atlantic pacemakers, you see the net surface heat flux is pretty small, but the biggest is the ocean dynamics, which is negative. So you're getting net ocean divergence in the surface layer, and this is contributing to this negative, is the biggest contributor to this kind of negative sea surface temperature anomaly, which gives you this opposite sign response in the Atlantic pacemaker. So just to summarize this, so the Atlantic response to the Pacific pacemaker over here on the right, you get these mid-latitude contributions that weaken the trades and warm the surface, and that contributes to this positive net surface heat flux because you're reducing the wind speed and the evaporative cooling. So that gives you that's the biggest contributor to the positive net surface heat flux. And you're also getting this ocean dynamical response. You're getting ocean heat convergence to warm the surface layer from the anomalous weak easterlies that are going on in the tropical Atlantic. Meanwhile, in the Pacific, the cooling contributions are mainly coming from ocean dynamics, ocean heat divergence in the surface layer, and the easterly anomaly surface winds from the anomalous walker circulation are the big contributors to that. So that's kind of the fundamental differences between the two and why you get these two different responses. Okay, this is all really nice because these are from these kind of idealized pacemaker simulations, but the question is, could you actually see any of this in any other model simulations that aren't pacemakers, or could you see them in the observations? So this is what we looked at. We looked at the 1800-year large ensemble pre-industrial control run. So this is 1800 years of simulation. We just did lag regressions from this model. So in other words, there's no change in external forcing. The model is just running along on its own, fully coupled everywhere. There's no pacemaker or methodology applied anywhere. And if the PDV is leading by 3 years, when it's positive in the tropical Pacific, you see the same sign in the tropical Atlantic, in the north and south of the equator in the tropical Atlantic. So that's kind of what we saw in the idealized pacemakers. If the AMV is leading by 3 years, when it's positive in the Atlantic over here, you get an opposite sign response in the tropical Pacific. So that's also what we saw in the idealized pacemaker. So that's kind of interesting that even in this large ensemble where the model is free running and there's no changes in external forcing, you see a similar kind of response. Which I'm going to talk about at the end. But even with all those things coming into play, if you do the same kind of lag connection, lag correlation, you see that you get this same sign response between the tropical Pacific and tropical Atlantic, and an opposite sign response if the AMV is leading between the tropical Atlantic and tropical Pacific. Now I just got a warning that my internet connection is unstable. So if I'm start freezing up, let me know. Okay, so what could be happening? Well, let's think about this in an idealized kind of way and how we can envision this, this kind of mutual interaction. So if we say that, of course, these are not oscillatory kinds of things, but I'm just putting this on here as to illustrate these things. So if you had an idealized AMV decadal variability that was looking something like this red line, and you had some kind of idealized Pacific decadal variability that was this blue line, if you say the AMV was in its positive phase here, from these previous results we've seen, that would be trying to drive the PDV into its opposite sign response, would be driving it negative. But when the PDV got negative, we saw from earlier that it would be trying to drive the AMV into a same sign response, so it would be trying to drive it also into a negative phase. But then when the AMV got to be negative, it would then conversely be trying to drive the PDV into a positive phase. So it'd be trying to get it into its opposite sign response where the AMV would be, excuse me, negative and the PDV would be positive. And then when the PDV is positive, then it would be trying to drive the AMV into a positive phase to get into its same sign kind of response. So in this way, you can imagine if you were doing this in a kind of an idealized way, and if you were trying to visualize how this mutual interaction could actually occur, you could have the AMV would be driving the PDV, and alternatively, then the PDV would be driving the AMV, kind of be this alternate mutual kind of interaction between the two. So the question is, can we see anything like that happening in observations? And of course, like I said, this is much more difficult because of all the problems with the short record and external forcing and everything else. But here's an IPO index at the top, an AMO index at the bottom. And with the naked eye, you can actually see some of these things. So like from when the AMV is negative here around 1920, It's trying to make the PDV go from negative to positive, so it ends up with a opposite sign response. When the MV is positive here, kind of in the mid-20th century, it'd be trying to drive the PDV into an opposite sign response. It would end up with a negative PDV and an opposite sign response. Meanwhile, the PDV, when it's negative, in this case, would be going from negative to positive, and that's when the AMV would be negative, and the AMV would be trying to drive the Pacific into an opposite sign response, and so on. So even with the naked eye, you can kind of see these interactions happening. And of course, this is why in those lag regressions from the observations, we were able to see something that looked kind of like what we saw in the long control run and in the idealized pacemaker simulations. So just to kind of summarize a bit more, again, what this could look like in another way in this kind of schematic. In this case, say we've got the AMV in its positive phase and it's trying to drive the Pacific to an opposite sign response. You'd get these positive precipitation and convective heating anomalies here in the tropical Atlantic that would drive anomalous strong ascent. Then through this walk circulation, you have this descent coming down in here into the Pacific. That would drive these stronger trade winds and produce increased ocean heat divergence in the surface layer and cooler sea surface temperatures, which would then give you this opposite sign response. If the Pacific was driving the Atlantic, in this case, say the Pacific is PDV and is in its positive phase, you have weakened trade winds, strong convection and precipitation over here over this warmer water. You'd get this stronger upward vertical motion, some descent coming down in the Atlantic, which would give you these kind of weak southeasterlies because it's not nearly as strong a descent as it was in the case over here for the Atlantic driving the Pacific, but it would actually then contribute to this. But another contributor to this is these PNA and PSA patterns here that are Rossby wave responses to the convective heat anomalies over the positive PDV SSTs in the Pacific. Excuse me. That would produce this anomalous lows in the North and South Atlantic, weaken the trades, reduce latent heat flux, warm the surface, and this would contribute to these warmer sea surface temperatures in the tropical Atlantic, which would be the same sign responses in the tropical Pacific. So that's how one way you could interpret this as how it may be working. But it gets complicated, as you can imagine, because when you start introducing external forcings, then it becomes, you have more than one thing going on with just the interaction between the Pacific and the Atlantic. So let's just take a look at a couple case studies. Let's look at this case here, looking here on the right here, when the PDV was positive here in around in the 80s and 90s, and you would say, okay, if the PDV was positive, it'd be trying to drive the AMV into the same sign response, so the AMV would then be driven from negative to positive, so you'd end up with the same sign response if the Pacific's driving the Atlantic. And so let's just look at this time period here, 1975 to 2000 in the time series pacemakers. And this is kind of a complicated plot, but we can start here at the top, and this is now looking again from 1975 to 2000, and this is the observed trends from that time period, and you'd see the same sign response. Tropical Pacific and tropical Atlantic are both positive. This is the trend over that time period from the large ensembles. This is, you can interpret this as the externally forced response. And of course, as you can imagine, it's kind of warming up everywhere. Have small positive SST anomalies almost everywhere. Now here's the Pacific pacemaker experiment where we've specified the time evolution of SSTs over this area in the Pacific. And we're getting a same sign response in the tropical Atlantic, which is what you'd think you'd expect if the Pacific is driving the Atlantic. And okay, is the external forcing coming into play? Let's subtract the external forcing in this upper right panel from this panel C here. And this is what you get when you remove the external forcing effects. And you still get the same sign response between the tropical Pacific and tropical Atlantic. It's weaker, but it's still there, indicating that during this time period, the Pacific is probably trying to drive the tropical Atlantic. Now, if you look at the Atlantic pacemaker, where we're specifying the time evolution of sea surface temperatures in this area, you're seeing, as you can imagine, because this is positive, you're seeing this opposite sign response in the tropical Pacific. If you subtract out the external forcing, you're still getting this more or less opposite sign response in the tropical Pacific and the tropical Atlantic, which didn't actually happen in the observations, but we did get that in the Pacific pacemaker. So the conclusion from this time period is the Pacific was likely driving the Atlantic. Now the aerosols are always kind of an issue, and in this case they didn't seem to play much of a role. If we fix the aerosols in the Atlantic pacemaker experiment, we're still getting the same kind of opposite sign response that we got when the aerosols were time varying and when we removed all of the external forcings. For the Pacific, you fix the aerosols and you're still getting the same sign response, which resembles in some way the observation. So the aerosols probably didn't play a big role in that time period, but let's look at another time period where the aerosols probably were playing a bigger role. This is the very recent period. This is when the AMV was positive, so you'd expect that it would be trying to drive the PDV from positive to negative, is what we're showing here. This is from 1996 to 2010. So let's look at the time series pacemakers from that time period. This again is the observations, the trends from 1996 to 2010, showing this negative IPO and this opposite sign situation here between the Atlantic and the Pacific. This is the external forcing trend from that time period. It's kind of warming up everywhere. This is the Pacific pacemaker, and it looks like, oh wow, it looks like we're getting something very similar to what we saw in the observations with this opposite sign response, but that can't be because the Pacific would be trying to give a same sign response. So when you subtract out the external forcings, well, sure enough, the Pacific is trying to produce this same sign response, but it's not because there's something about the external forcings that are contributing to this warming that's going on here in the North Atlantic, at least in this Pacific pacemaker experiment. Now, if we look at the Atlantic pacemaker, and now we're specifying the SSTs over this region here in the North Atlantic, oddly enough, we're getting a same sign response in the tropical Pacific, which is what you wouldn't expect from if the Atlantic was driving the Pacific. You'd expect that the Atlantic would be trying to drive us an opposite sign response. If we subtract out all the external forcings, you're still getting the same sign response. But what if we fix the aerosols? And we fix the aerosols, now you're starting to get this opposite sign response. It's pretty weak and it's kind of not quite in the right place, but you're getting the sense of this opposite sign response that the Atlantic is trying to produce that you don't see in the Pacific. The Pacific, if you fix the aerosols, you're still seeing this opposite sign response. So I think this just illustrates the fact that the aerosols are playing a bigger role in this time period in producing this kind of a pattern that's superimposed on top of the internal variability that's going on, that kind of makes it more difficult to interpret these finite time periods in the observations. And of course, then this also has implications for initialized predictions. So just to summarize, I showed you that we use two types of pacemaker model configurations, an idealized, where you put an idealized pattern of decadal timescale SSTs in, and a time series where you have time evolution of SSTs over a certain region. For AMV and PDV, and of course the rest of the model is fully coupled. And the reason we do this is to try to disentangle these cross-basin interactions to see what's forcing what between the tropical Atlantic and tropical Pacific. And the pacemaker results that we ran kind of confirmed some previous results, which is reassuring that when you specify AMV SSTs in the Atlantic, there's an opposite sign SST response in the tropical Pacific. And when PDV SSTs are specified in the Pacific, there's a same sign SST response in the tropical Atlantic. So there's a fundamentally different kind of response between the two, depending on which ocean basin is driving the other. And this was confirmed by an analysis of a long control run and also from lag regressions from observations. And we showed that the reason this is because the net surface heat flux in the Atlantic plays a bigger role as connected to that mid-latitude teleconnection pattern that produces anomalous low pressure centers in the subtropical North and South Atlantic that weaken the trades there. And that gives you, reduces the latent heat flux, which contributes to warmer SSTs. And you also get a little bit of a ocean heat convergence of heat from the weakly strengthened southeast flow on the surface in the tropical Atlantic. So this all led us to propose this new paradigm for decadal timescale variability, such that we're proposing that the processes in the Pacific and the Atlantic, tropical Pacific and Atlantic, are mutually and sequentially interactive. This occurs mainly through the atmospheric water circulation, but also gets contributions from mid-latitude teleconnections for the Atlantic response to the Pacific. So we started out by saying, well, would it be possible that if we could just capture and predict processes in one ocean basin, then that would drive everything else and it would simplify our lives for the initialized decadal climate prediction problem? Unfortunately, that doesn't seem to be the case from the evidence that we've shown today. It shows that we've got to actually be able to predict processes and mechanisms in both basins and their interactions to get credible decadal climate predictions over the tropical Atlantic and Pacific, and then with their associated large-scale teleconnections with implications for precipitation temperature extremes over land in the Indo-Pacific region and beyond. So thank you very much.
Great, thanks for that, Jerry. That was really fascinating and really interesting. I've got a few questions that have come through, so I'll start from the top. From Ian McAdam, if you're using coupled model pacemaker experiments to look at internal variability, do you need to make sure that the control and the perturbation simulations have the same amount of energy within the climate system?
Yeah, that's that's an interesting question. That's been one of the criticisms of these kind of pacemaker methodologies, is because they're not strictly energy conserving. You don't want to put in the SST patterns directly. You usually nudge them in some way, or you change the net surface heat fluxes in a way so it's not that huge a perturbation to the system. But strictly speaking, they're not totally energy conserving. That's one of the weaknesses of this methodology. But that being said, that's a caveat. But I think you saw that by doing the pacemaker simulations and then comparing the lag regressions from the long control run, we saw basically the same kind of response. So I think these pacemaker experiments can be used as a tool, but with that caveat about energy conservation. And again, that comes down a lot of ways to the details and how you put in or how you get these specified SST patterns.
Great, excellent, thanks. Tess asks, in the A and B pacemaker runs, the SSTs are prescribed only in the Northern Hemisphere, and the PDV runs, the SSTs are prescribed both north and south of the equator. Firstly, why is this? And secondly, if the A and B runs have prescribed SSTs in both hemispheres, would the results change?
Yeah, interesting question. We basically wanted to specify for the idealized pacemakers in particular, that was kind of the starting point, the kind of AMO pattern, which is defined as from the equator to 60 north. That's kind of from the literature. So we wanted to actually, that was our starting point. For the Pacific, we wanted to do the IPO, which is usually defined from for the whole Pacific basin. So that was kind of the motivation behind using those areas for these, for the idealized pacemakers. For the time series pacemakers, we actually were using just that Kasaka and Chi area in the kind of tropical Eastern Pacific, not the whole Pacific basin, but we were using the whole AMO area in the Atlantic from equator to 60 north for the time series pacemakers. So it turns out that, as you expect, and the literature was looking at other pathways of how these basins could interact through the mid-latitudes, and those are still possible pathways. The biggest one, of course, is always through the tropics, and so we ended up focusing on the tropical Pacific and tropical Atlantic mainly. We did get a mid-latitude connection through the teleconnections for the anomalous Rossby waves that come from the Pacific back over the Atlantic that influence the Atlantic. But I think if we would have specified the entire kind of Atlantic for our idealized pacemakers, it would have been positive. When the AMO is positive, it's negative SSTs in the South Atlantic. But as I think in the end, it would have turned out, and I didn't point that out, but it turned out that you do end up getting negative SSTs in the South Atlantic when you just specify the SSTs in North Atlantic. So, and that's due to energy balance considerations and how the anomalous wind field is affected and the latent heat fluxes and things like that. So I don't think it would have been, since it boiled down to the tropics for both of these sets of experiments, I think it wouldn't have made that big a difference.
Okay, great, good response. Really interesting question as well. Andrea asks, model experiments show that Indian Ocean SST forcing can drive changes in the Pacific Walker circulation. Do you think the Indian Ocean may play a role in modulating these Atlantic-Pacific interactions?
Yeah, that's kind of the next thing we'd like to look at, and of course, and you're right, Andrea, that the Indian Ocean can play a role in this, as you and others have shown, because when we looked and we did a set of Indian Ocean pacemakers, the idealized Indian Ocean pacemakers weren't that interesting because it's just, there's such a huge trend in the whole Indian Ocean SSTs over this time period. The time series pacemakers for the Indian Ocean kind of confirm previous results that when the Indian Ocean is trending positive, it's strengthening the trades in the Pacific and producing this kind of opposite sign response between the Pacific and the Indian Ocean. And then that kind of feeds back to affect the Atlantic, but how the Indian Ocean directly affects the Atlantic versus indirectly through the Pacific. There's Jishin Lee had a paper where he was proposing this kind of multi-stage interaction across the basins, and that's a possibility as well. And I think that's kind of one of the next things we want to look at, is to try to bring the Indian Ocean into this, especially how the Indian Ocean and the Atlantic could be actually interacting separate from the Pacific.
Interesting. Thanks, Jerry. Dongjia Yang asks, why is there a big seasonal difference in terms of the East Atlantic response to PDV? For example, in your experiment AMJ1, the ocean heat advection is -0.6, but in JAS1, it is 0.3.
Yeah, that's kind of a that we were trying to struggle with how to look at that, and we're kind of following that the analysis that Rupert Robert et al. Did, where they were looking at the first year of those 10-year idealized pacemaker simulations. And what happens is when you just start this out, when you put this pattern in, the system is kind of shocked. So it takes a few seasons for it to kind of sort itself out. So that's why we were looking at kind of just the last couple of seasons. And depending on how you calculate these heat budgets for the ocean, over what depth and we tried different depths, we tried different ways of calculating it, and no matter how we did it, and the magnitudes changed depending on how you did the details, the thickness of the layers and things like that. But the main result was always that the net surface heat flux was always a bigger contributor to the tropical Atlantic response to the Pacific forcing, whereas the ocean dynamics were the bigger response for the Pacific response to the Atlantic. So yeah, you can do it different ways, and we tried it a number of different ways, but the main result was always the same.
Cool. Shane McGregor says, thanks for a great talk, Jerry. You showed a strong consistency of evidence between models looking at the idealized interbasin interactions. I'm curious as to whether you think we would see a similar consistency with time evolving SSTs.
Well, maybe Shane could clarify that a little bit, because we had both types, right? We had the idealized and the time evolving SSTs. And I think with the main difficulty in interpreting the time evolving sea surface temperature, the time series, what we're calling time series pacemakers, is we've got time varying external forcings. And so, volcanoes are going off and you have changes in aerosols that are geographically different. And we actually in the paper looked at some of our previous experiments where we were just looking at the single forcing experiments to see if we could help interpret what was going on in these different time periods. And depending on when you look at in the time periods, you look at different trends at different time periods. The problem with the aerosol forcings is their time variations are different geographically between Asia and say Northern Europe and North America. And so it's really, when you start looking at the aerosols, the time periods become really critical as to which time period you're looking at over what region. And so that's why we ended up just showing kind of two case studies, one where the aerosols didn't seem to make a big difference, but the other one, when the external forcing did seem to make a difference, just to illustrate the fact that the external forcings just complicate everything in when you're looking at time series pacemakers and in the observations, because obviously the observations have time varying external forcing also.
Okay, cool. I think so. Shane, had you clarify quickly? I was wondering. It was whether doing the time varying experiments with different models, you would find the same or similar results.
Okay, with different models. That's a good question, and that I think some people are starting to look at that. The DCPP experiments as part of CMIP6 have some of these experiments, have some of these pacemaker experiments that were done in a similar kind of way. I think from what I've seen so far, there's been a couple people have looked at these. There is a real model dependence on how this actually works in terms of magnitude of the signals that you see from depending on which is forcing what. And it's as you'd expect, there's always differences in the way models respond, and I think that's kind of one of the challenges is when you move into a multi-model kind of analysis space, then you've got to really understand what each model is actually doing with these processes. And so it becomes more complicated. That's kind of why we started out just looking in one model where we thought we kind of understood it, or at least we assumed we understood it. We probably didn't really understand it, but it gave us a hope of trying to diagnose these things in these very complicated coupled systems in one framework with the model run in a variety of different ways. So I think the next step would be to actually do more analyses on these multi-model data sets to see how model dependent these things are. And I think that's why we kind of did it in this way. We kind of proposed this paradigm for this mutual interaction, and so other people can test it and see if it actually shows up in other models.
Yeah, it's really interesting. I'm really interested in those results myself. Ryan Holmes asks, you kind of touched on the amplitude in your response just then, but you talked mostly about the phasing or sign of the PDB and AMB. What about the amplitude? The interaction mechanism may be a way to generate variability. Has anyone done partially coupled experiments where they suppress or enhance the PDB or AMB and look at the variability amplitude response in other basins? That's
an interesting idea. We experiment a little bit with changing the amplitudes of especially the idealized pacemaker experiments. And as you'd expect, in this single model, we just could scale up and down the response. The magnitude of the response would depend on the magnitude of the forcing. I think the real challenge in these kinds of things when it comes to magnitude is you're looking, especially in these pacemakers, and I think this was one of the things, another caveat that has to accompany these pacemaker experiments is I think when Kasaka and she first published that paper 8 years ago, there was this wave of enthusiasm that, all right, now we have a way to actually disentangle all of these complicated interactions across basins and globally and everything else. But there's all these kind of caveats that you have to accompany it, because the pacemakers by definition are only responding, the rest of the system's only responding to what you're putting into this one area. So you can't get this interaction. So if the magnitude of the responses are actually dependent on the interaction, you can't get that in a pacemaker methodology. We saw when we analyzed the lag regressions in the long control run, we actually saw a little bit bigger amplitudes in the response areas. I didn't point that out, but we got a little bit bigger amplitudes indicating that the interaction was important to get the amplitude. But again, that's in a different configuration of the model and everything else. So I think that's the amplitudes of these things are a real challenge. And one of the interesting things about amplitude that you probably noticed, I may have forgotten to point it out, is that in the Pacific pacemaker, when we're specifying the Pacific forcing, the tropical Atlantic response is pretty low amplitude and much lower amplitude than you'd get in the positive phase of the AMO. And it's spread across the whole tropical Atlantic. It's not just north of the equator, it's for the full Atlantic, full tropical Atlantic. So in this, strictly speaking, you can't say that the Pacific is driving the AMO. You can say that the tropical Pacific is probably driving the tropical Atlantic, which in the tropical Atlantic, the north of the equator is part of the AMO, but this could only be one contributor to this kind of thing that people think exists, is called the AMO. But the kind of sidebar to this is that when people are trying to string together mechanisms for Atlantic decadal variability, the AMOC is always kind of high on the list. But the biggest connection to the magnitude of the AMOC is to the subpolar gyre way in the North Atlantic, not so much to the tropical Atlantic. So this is a tantalizing result that maybe the Pacific forcing could fill in the tropical Atlantic part of this AMO pattern, and it would supplement the AMOC. So that's another kind of possibility that would be an interesting thing to look at.
Cool. So Craig Bishop is asking, what are the timescales of interaction?
Sorry, I meant to say, in your description, I couldn't really understand what was causing the timescale of the transitions. You're talking about a decadal timescale, but when I think of the response in like effects on the Walker circulation, I would imagine that would be quite quick. So could you explain a bit more about what's making it so slow?
Yeah, so that gets into the mechanism question. And I think papers like the ones by Andrea and others were looking at on the interannual timescales, you see some of these same connections. And some of those pacemaker experiments that I showed were looking at the interannual timescale where you see the same thing. And you're right, the Walker circulation does respond pretty quickly. I think the piece of this that there's a couple of things that make it somewhat slower. One is that when you kind of force the ocean, you get these kind of slow Rossby waves that are off equatorial that can actually introduce kind of a longer time scale to these fluctuations. So you can start them out on a kind of a short time scale, but then you get the ocean that kind of then responds on a slower time scale. And you also, to get this kind of PSA and PNA pattern that can be sustained, and of course these decadal timescale patterns have interannual timescale variability superimposed on top of it. So you're having ENSO events kind of going on, and then you have this kind of slowly varying background base state that's then producing these slower kinds of interactions. And so these kind of slow things, if you get a sustained convective heat anomaly that is there more often than not over, say, a 5-year period, then you can get these kinds of the PSA and PNA patterns that would be there. They're not there constantly, obviously, but they could be there enough that would then affect these slower responses in the tropical Atlantic that would then give you this kind of decadal timescale to it. So you usually have to invoke ocean processes that can give you these responses. And obviously the atmosphere is a lot faster, so the atmosphere kind of gets these things going, and then the ocean kind of responds and then produces this slower timescale. Okay. Or at least that's one interpretation of it.
Cool. Alex had another question on timescales, but I think you've kind of answered that as well. I think our last question, there's been some really interesting questions, but I think we'll finish on Scott Power's question. Do you see a robust relationship between the North Atlantic and the THC index and IPO series in the 1800-year control run too?
Sorry, could you repeat that question?
Yep. Okay. So, Jerry, do you see a robust relationship between the North Atlantic and the THC index and IPO series in the 1800-year run as well?
That's something we haven't looked at, but that's something that was it would be interesting to look at that, because that would then, you could look at it in the control run and then try to do the same kind of analysis in the forced runs, because there's all kinds of ideas about how external forcing can be affecting the manifestation of the AMO and how that could affect the AMOC or the THC, and how that connects to the Pacific. And there's some work going on in our group actually looking at the PMOC, the Pacific Meridional Overturning Circulation, and the AMOC, and how they may or may not be connected through the tropics, and kind of taking this kind of idea to the next step where you actually are bringing in Pacific ocean dynamics more fully, and how that relates to the Atlantic AMOC. And so I think that's something that we're starting to look at, but I think that's a real interesting kind of part of this as well.
Excellent. Thanks for that. That was a really interesting discussion and bunch of questions. And thanks, Jerry, for keeping to time as well. So with that, I might close this